see the slides, right? But they can't hear. The audio is the problem.
No, I think they can hear as well. So let me do something. Okay. So Janine, to confirm, you can hear and see the slides, right?
Yes.
Okay, great. So we're gonna start.
Yeah.
Okay. All right. Hello, everyone. Welcome to ESIC seminar. Today we have our own Dr. Anjan Bose. He will be talking to us about grid control challenges, reliability, and resiliency. Dr. Bose is a Regents Professor and the Distinguished Professor of Electrical Power Engineering at Washington State University in Pullman, where he also served as the Dean of College of Engineering and Architecture from 1998 to 2005. He's a fellow of National Academy of Engineering. Dr. Bose also served the US Department of Energy as a senior advisor on the electric power grid during the Obama administration. He has worked in the electric power industry as well as in academia for 5 decades. He received his bachelor's, master's, and PhD all in electrical engineering from Indian Institute of Technology, Kharagpur, University of California, Berkeley, and Iowa State University, respectively. Thank you for the seminar today, Dr. Bose, and back to you.
Okay, all right. That's so I'm as you can tell, I'm using some slides that I use somewhere else. That's because I'm not going to go through all the slides. Actually, I just used these slides last week for sort of an international webinar organized by the Chinese Society of Electrical Engineering, and some of you were on there. I know Menuka was on there. You were on there. So I won't repeat everything. Okay, so but let me tell you what I want to kind of get across is that every one of you are quite aware of the fact that we are trying to shut down all our greenhouse gas producing generating plants and replacing them with more clean renewable energy. All right. So there's seats here, seats over there. And so the question arises now, the Biden administration wants to have the US be carbon neutral by 2035. Other countries, many countries have longer periods to do that. But the question that very few people seem to be asking is whether this grid that will look very different in 15, 20 years, who's going to run that grid and who's going to make sure that the lights don't go out, right? So that's, I will only cover a little bit of this question, but I want to put it out, and I don't have any answers to the questions, obviously. I'm just going to put out the questions about system operations and control. But think about a much simpler question. All right, suppose, I mean, you guys will all be working in industry and within the next 5 years, well within this 2035. So you'll be working with this stuff as we change over. So suppose somebody comes to you and says, yeah, you have a PhD from Washington State University, so you obviously can be an expert, and tell us what, if we have to replace my 100 megawatt coal generator, how much, what are you going to do? Let's say, what renewables are you going to put in and how much? All right. So what's the answer? Or do you know how to even get the answer? Yeah, go ahead.
I'm gonna convert that to gas. That's the safest option.
Gas is not clean. Gas is not clean. You've got to be cleaner than that.
Nuclear.
Nuclear, yes. They're not allowing nuclear right? Nobody gets permits to build nuclears anymore, not in this country.
Yeah.
So how about if you suppose the question was, say we are in Eastern Washington and we have a lot of wind here, right? So how about wind generation? How much? 100 megawatts of coal. Now remember that coal, what?
I'll probably convert that to energy.
Okay, so energy is relatively easy. Coal is most often used as base loaded plant, right? So it runs all the time. So you multiply 100 megawatts by what, 7,000 some hours for the year, and that's your energy. Okay, so then tell me, what do you have to do?
Why nuclear is not allowed?
What?
Nuclear is not allowed.
Why? Well, that it's mainly politics,
Oh,
right?
I thought maybe there is some like engineer.
No. It's only in the US that we don't do nuclear. Almost many other countries do nuclear, but Germany has banned nuclear, and now, and all of us who were, but even in the US now, they're rethinking whether we should be shutting down our nuclears, because nuclear right now is about 20% of our energy in the US. Okay, and many of these plants are they're running out of their lifestream unless they're refurbished. And so the question, people are now thinking whether we should keep it going, but nobody, actually there's 2 nuclear reactors that are going to go into service in the South, in Tennessee, I think, or Tennessee or Georgia. And those are the only ones that are being built in the last 40 years or something. Okay, so all right, so let me go back to the question of how much wind do you need? Energy, you said. That's a good answer.
Well, the problem is that it's variable, right? So we're gonna need more actual
Yeah.
capacity for the turbines that we put in for wind, let's say.
Right.
And you'd want the average to equal
Yeah.
the base load of the coal.
So let's say the wind only blows,
Yeah,
let's say a quarter of the time. Right. So you need 4 times, right? 4 times as much energy for so if you put up 100 megawatts of wind, that's not going to do it, right? So you put up 4 times as much, right? 400 megawatts worth of wind. Then you'll get enough energy, right? But at the wrong time. So then what do you have to do? Okay, all right. So you buy a bunch of batteries, right? And so 3/4 of that energy you have to now put into batteries. So now you run into the next problem is, so how big are those batteries? Right? Because you have to, it's going to be 75% of the time it's going to run, but then, it goes up and down and so on. So anyway, but that's only the beginning, right? Now you go around and change everything around, and you get all these wind and solar and batteries. We hadn't thought of we don't even know how to operate batteries, right? Run batteries. So now you've got this new system, and you're going to now operate it. Okay, so now these things operate somewhat differently than the coal plant you just shut down, right? These renewables are turned into DC, right, and produce DC, and then back into AC to put on the grid. Right? So it's not like you don't have VARs like you do in a coal plant. All right, you don't know you have to put them up and down in the coal plant. You run it for AGC, you give it a little, you ping them with control signals, and it goes up and down, right? So you have to figure that out for your renewables. So that's why I thought, instead of worrying about that first problem, which obviously nobody has figured it out very well yet, right? Because you know that last month, not last month, 2 months ago, in the summer, California ran out of electricity. And they had to, and I don't know if you saw the video, you must have seen the news reports on that. The videos of the CEO of California ISO appealing to Californians to turn down their thermostats and not to turn on their electric vehicle charging, and so on. So it was actually portrayed by the state and the governor as being such a wonderful thing to have done, except I thought it was rather shameful, at least from the engineering point of view. but so, but I thought we'll leave that one aside, because that's a harder problem than what I'm going to tell you now about if you had a completely non-carbon electrical grid, how will you operate it? How will you control it? So let's. So I'm not going to go through this. This is just sort of a description of what the new grid is going to look like. The main thing to remember about the new grid is that it'll have a lot of small generators distributed much more widely. So what in the old days, or even now, would be 100 generators will probably be replaced by 1,000 littler ones, right? And most of them will also be connected through this DC to AC and all of this kind of thing. All right. So just think about that. That is, some of these generation, instead of being connected to the transmission system right now, before all generators were only connected to the transmission system. And in the old days, nobody was allowed to actually generate electricity except for your own self. Okay, now you can generate electricity and stick it on the grid. All right, this got allowed some years ago. Okay, so so let's talk about how do we operate the grid, and so a few control things. There's the automatic control. There are things that are controlled automatically. AGC is automatic. Right? No manual intervention needed. Okay. The voltage control is automatic. And in this country, voltage control is almost always local, meaning the voltage at some point is measured, and it sends a signal back saying this is too low, and the nearest generator or transformer or something changes its taps, changing its voltage setting, and controls the voltage. In many other countries, they do regional voltage control, right? Like very similar to AGC. Okay, and that may come into play here too. And in fact, it'll probably become more common because you've got so many generators that you can't expect that a substation level generator is going to be held up by only one generating source when you've got so many small generators. But those voltage controllers, whether they're local or regional, they're still automatic, right? The operator has nothing to do with it. Then the manual control. I mean, we have these operators, both at the transmission level and at the distribution level. You have the EMSs at the transmission level, DMSs at the distribution level, where operators are sitting in front of consoles and measurements are coming in and they're watching it, and they can make changes. What can they change? Okay, one simple one is obvious one is the switches. Okay, you can open and close breakers. Right? But there are other things you can change. Who sets these? Let's say you've got a voltage controller that wants the voltage to be at 1.03. Right? Somebody sets that. Why not? Why is it 1.03 and not 1.01? Right? And the reason is somebody said it, you said it beforehand by your voltage studies and said it's got to be 1.03 over here because by the time I control the voltage at the end of the line, it's probably a lot less and so on. So the operator can actually change that voltage setting. It sees the voltage is going down, you can raise the voltage setting at these places. So you also have to change the generating reserves. Right? At any given time, you have to have generation that is reserved. So your one generator shuts down, you have to have enough generator. So these are the kinds of things that the operator does. So the operator, most of the time, if you go into a control room, you'll see that most of the time they're not doing anything. And they're just watching numbers or reading comic books or whatever. Right? And then suddenly there'll be something go wrong. And usually the operator will have, voltage will go out of limits or some thing will trip in your system. And suddenly, your screen will start flashing, your alerts are going to buzz, and then the operator wakes up and they have to start doing things, right? So that's manual control, right? Now there's a lot of talk and a lot of papers written about why we should make everything automatic, but nobody's figured it out yet on how to do that, right? And then there's the whole bunch of controls that is outside this domain, meaning, see, think of protection control, which is actually things that are out there that operates because of certain conditions that occur, right? So you trip a generator because you suddenly get a short circuit and you're getting an overcurrent on your generator, then you trip the generator, right? So that's the kind of protection systems. And what is happening now? So the two areas where things are moving pretty fast is that protection used to be very simple. Okay, overcurrent protection and distance protection, these kinds of things, right? And now, of course, they have these special protection schemes, which because you can now bring in a lot of what you can do today is to bring in data into a protective system, a protective relay from far away, right? Which didn't used to be the case. It used to be mostly local, but now you can say, well, you can, and now you can even get PMU data to feed into the relays. So suddenly, if you start seeing that your angles are moving too fast away from each other, you open up the breakers, or you open up the line where you're going unstable, and so those are called special protection schemes. As you know. And then the other big problem that people are facing is this whole idea of these generators being all over the distribution system. People are attaching whole bunches of small generators, renewables, which means that before power always flow in one direction from the substation down to the loads. And now you've got generators on the distribution system. So now you don't know which way the power will flow. And there are whole areas of Southern California where during the day, when people are out of neighborhoods in suburban neighborhoods, during the day when and all of these things have sunroofs, photovoltaics on their roofs, there's power flowing into the grid. Okay, so instead of power at the transmission substation, instead of the power flowing in towards the loads, it's flowing now in the opposite direction. What this does is your protection system has to adjust to be able to handle. Okay, so now what could be power, could be currents going in one direction, could be, you might have almost the same amount of current going in the opposite direction. Now figure out how you're going to do your overcurrent protection. Which way, which current are you going to protect it from? Okay, so so what are the challenges here then? So I mentioned a couple, but the big problem with automatic AGC is that now instead of having to ping 10 generators, 20 generators, or to go up and down to stay up with the load, now you might have to do 100 generators or 1,000 generators. And that requires you to divide up these controls further and further as you go down to the lower and lower levels of generation. Okay. Right now, what you do is you get an AGC signal. You all know the ACE. You calculate your ACE. You say, well, now I divide up the ACE into the 10 generators that are helping me, and I ping those generators, and I tell those generators what to do. And now you have to do, well, now you've got to say, well, it's got to be 1,000 generators. Okay, so now, so the one thing that's in our favor is that this is relatively slow control, right? 4 seconds update of these things is the common thing. 4-second measurements coming back, 4-second measurement control signals going out. So, but here I'm coming up to the real thing is that AGC is done at the balancing authority. Balancing authority is often the whole ISO. So if you think of the Midwest ISO as a footprint, is a huge amount of the Midwest, right? You're trying to then balance the load and generation of the very large area. And the only way you can do this now, if you have, let's say, 50% of your generation on the low voltage side, right? You'll have to know what the hell is going on in the low voltage side. Right now, nobody sitting at the Midwest ISO EMS have any visibility of what's going on in the distribution side. Their last measurement that is coming, their lowest voltage measurement is coming at the lowest voltage transmission system. So you see why this is a challenge. And the question is, you can't expect the guy sitting in what is MISO's control center? It's in Indiana somewhere, right outside Indianapolis. Yeah, and so you can't just drown him with thousands and thousands of pieces of generation data every second, but as I said, the AGC part, of course, is invisible to the operator. But even if this data comes in directly from all these things, it still has to go through several control centers. Right, the data from the distribution system is coming into the DMS. The DMS talks to the EMS, first level EMS at the transmission operator. Then that talks to the ISO EMS. Okay, so you've got a whole bunch of these things, and this movement of data between DMS and EMS has never been standardized. It's still being worked on. Okay, so it's a huge challenge. And in fact, all over the world, people are talking about how to do better TSO-DSO coordination between the transmission side and the distribution side. And this is not just about the AGC one is going to be done automatically. Okay, but everything else, all the manual stuff, you have to have coordination between the operator at all these levels with the DMS operator. And right now, the distribution side just sort of operates, and the EMS side, the transmission operator just reacts to whatever they're doing on the distribution. It's on the other side. You can make decisions without knowing what's going on. And that's a big difference until now. When we didn't have this generation on the distribution side, distribution was considered passive, right? The only thing that changed was loads. And you could watch the changes in the load at the transmission substation and the feeder loads, right? And so then you said, okay, fine, that was good enough. But now it's not. Now you have to decide what to do inside the distribution system, and some of these decisions have to be made at the transmission level, sent down to the distribution level, and so on. So that's the one big issue that most people don't realize, is that with generation being on the distribution system, everything looks like one system and not transmission system and distribution system separate. Okay, so I already talked a little bit about protection, but here's the other thing. Right now in the US, the load's not growing. The total load consumption is not growing. This is also true in Europe. All the developed countries, the loads are not growing. So, except now two things are happening which will make the load grow. One is the EVs, right? That's going to make the load grow, because that's what we're going to see is the energy that goes into transportation in the form of gasoline is going to come out of the electric grid. Okay, so that's going to be one major one. And now there's pressure on a lot of the other industries, whether they're chemical industries, they're pharmaceuticals, they're whatever industry, steel plant, cement, everything uses huge amounts of carbon-based heating. And they're being under pressure to move to electrical. So, if you think about the timing of this, it's kind of weird, because the assumptions that all these industries are making is not just that going to electrical will be cleaner, but that the grid itself would be clean by the time they make their conversion. Okay, so that's a big step. Who's taking care of that? Because right now, people feel good. I talk to lots of people. I just bought another Tesla. This big bragging point, which says you're rich, but but it also makes them feel good. They said, I'm doing this for the environment. I said, yeah, but if you live in Atlanta, 80% of your electricity is coming from coal. So how good can you feel? So yeah, someday I guess they're going to change over, but this is why the developing countries are in a much worse condition, because their load is growing 6 to 8% every year anyways, without all this other stuff coming onto the grid. So consider that you're not, now remember we talked about, 100 megawatts of coal plants shut down, meaning about 400 megawatts of wind plus thousands and thousands of megawatt hours of batteries, right? So consider that if the load is also growing at the same time in China or India, no wonder they don't want to do anything until 2070. They can't. Let me talk a little bit about this other thing that's coming into play, which is resiliency, right? So I know many of you are working on resiliency, but the question really is, why isn't the reliability that we have been designing for the last 50 years, why isn't that good enough? Right? Why?
Care about resiliency.
Right.
It, reliability, we measure how system by the surface customers. A resiliency model, how fast system can cover to.
Good. Good. Yeah, that's right. So think about reliability now. By the way, I don't know how many of you are realize it, but the reliability of the system, of the grid, is the rules for reliability, the measures of reliability are set at the transmission level by NERC and FERC, right? And so they give rules, and for the bulk power system, for the transmission, and there's essentially from an engineering point of view, there's two areas that you have to worry about. One is that you have enough generation to cover your load, and the measure of that is what is called the loss of load probability. That is, you shouldn't get into a situation when you don't have enough generation once every 10 years. Okay, not more than that. All right, so that's the rule, and this is goes back to the question I had first asked. When you replace the 100 megawatt of coal with so much of that's what you have to meet, is that you have to have enough generation, and it doesn't matter whether it's wind or solar or nuclear or whatever, that it has to be more than your load. Okay, and then the other thing is if you have enough transmission. So you want to make sure that whatever the load and generation distribution is on your power grid, that if you lose one major transmission line, that won't overload everything else. Right. So that's the N-1 rule. Right. So those are the two major rules that people follow for reliability. And then on the distribution side, they actually use more long-term measurements over time to look at the frequency of outages, right? So the distribution, the measure is different, but the distribution side measures are not set for NERC, right? It is set by each state, by the PUCs. They look at these numbers and they say, okay, so you need to do better than this or whatever. And it's a slow, long-term process because you're collecting data over time. As Lindley said, these are all preventive measures, meaning that if you meet these measures when you design your system and operate the system and make sure these measures are met, then you're unlikely to have a major outage. Right. The problem is that you have a major outage not because of failures of the electrical system, it's because a hurricane comes and wipes you out. Right. And then the question is no longer how to avoid a major outage. It's a question of how quickly you can get back into service. You know, if you get 1 million people. So this is the issue about the resiliency is we don't, of course, if you have a reliable system, it's better. An unreliable system will be worse for resiliency, but a reliable system is not enough. Okay, so as Lindley said, the main thing about resiliency is you have to be able to recover and as fast as possible. And then resiliency, you know, people think of it somewhat like when the if a storm is coming, you get ready for it. And then once it happens, then you have to do the damage assessment. I mean, this is the real difficult part, is you don't know what has been damaged until you actually send out. And if your communication system is down, if your SCADA system is down because of the storms, then of course you have to send people out to know what to do. And then of course restoration is many times. I mean, if your distribution poles are down, you know, you can't do very much of connecting your loads, right? You have to wait until somebody digs and puts up the new poles. So here, you know, Katrina, before this hurricane hit in Florida, Katrina was the largest hurricane. This Ian was as big, and you know, one of the things I want to point out is that something like 1.1 million customers were lost from Katrina. You know, most of them in the New Orleans area in Louisiana, but some in Mississippi. The Mississippi people got out okay, you know, and this is in days. So something like between August 29th and September 22nd. So after about 3 weeks, when they were catching up, they gave up because the center part of New Orleans was underwater. There was nowhere to get them restored. So they basically said 200,000 people, like 200,000 customers, we can't do anything. So that's why this drop, which says that we're not going to do anything about them. And then the rest of them got, but it took a month, more than a month for things. And those 200,000 people, you know, many parts of that area were so devastated, and some of them haven't built their houses back in that area. Okay, so that's the problem with the with resiliency, and the issue to think about is cost. Everybody wants a resilient system, right? But how much are you willing to pay for it? Right? And this is why we need to have some measures of resiliency. See, you can't say after the hurricane hit that you should have been able to withstand that hurricane, right? You have to know now what to design into your system that can withstand a level 4 hurricane, all right? Then, okay, once you have that as a measure, then you can put in the strengthening things that you need, and then you can go to your state or whoever regulates your rates and say, look, we had to put in so many hundreds of millions of dollars worth of strengthening of the distribution system, and and then they look at the number and they may say that, well, that's too much, you know, your rates are going to double if you do this. And so then they'll say, all right, so let's do little less than that, okay? And you live with the fact that if the hurricane is worse than that, then you don't come back up, all right? The problem is worse because, you see, these extreme events are localized, meaning some parts of the country don't have hurricanes, so we don't need to do hurricane. Okay? Other parts of the country have tornadoes. Some parts of the country have earthquakes. You know, we in the West have these horrible fires. Okay, and you know, California is struggling now to figure out what to do about these fires. Actually, Washington is as well. We just don't have that big a population that are complaining. As California does. So that's the issue, right? So the resiliency issue is somewhat different from the reliability issue, which we will have to take care of as these changes come about. The resiliency is going to be sort of, you know, in the policy arena for a while because nobody knows how much resilience you want. But people like to talk about it. You know, I mean, when Puerto Rico got wiped out recently, you know, a lot of pointing fingers at who was to blame. But then, you know, cybersecurity is another one that gets the attention of very high up people in Washington, D.C. Nobody knows what to do. Right? So on cybersecurity. So that's another area where somebody like NERC will have to come in and say, this is cybersecurity. You have to have this is what level of cybersecurity you're going to do. I mean, somebody's got to set the rules, and NERC is the one that will set the rules for that. And the rules right now are not terribly not strong enough. At least most people feel they're not strong. So let me stop there and take a couple of questions. Yeah.
So yeah, my question is somewhere around the secondary discussion we had on the ISO and balancing. For instance, they're having some resilience assessment. That's
Can
important.
you speak up? We have online folks who cannot hear you.
Yeah. So if you talk loudly,
Okay. I'll be as loud as possible.
Okay.
So you said like balancing authorities are somewhat local ISOs. So in terms of analyzing this from the perspective of resilience, if I want to analyze, let's say, some powerful analysis on the, let's say, hurricane, right? We have an advisory 15 days ahead, 20 days ahead. I want to see that how it's traveling and how I want to like the grid. Florida, then do I need to see it as an entire eastern interconnection, or how would I just study on this and how it has been done?
Okay, so many of these things like AGC are, you know, assumes that you're in a normal state, right? In an emergency state, in an abnormal state, you know, you probably don't have AGC. And if you think about this recovery business about resiliency, you know, one of the strategies is to be able to have microgrids that will survive on its own. Now, you know, people think microgrids is a wonderful PhD idea that somebody thought up, but actually, if you just go down the street here into the rural areas, you know, every house is a microgrid. They have a diesel generator which pops up automatically if their lights go out, which does very often because most of the people out in the farms have very stringy distribution lines connecting them. So this idea of surviving an outage is not new, you know, and hospitals and things have done it for all the time to do that. The question is, how automatically can it be done, and how it can help come back to put the grid back together again. Okay, I mean, if you're one house, you know, you just shut off your diesel generator when your lights come back. But it's a little more complicated when they had to do their own balancing, right? So this has nothing to do with the balancing that the grid is doing. But when they connect back on, this whole, you know, which is why a lot of people are working on this grid forming and grid following kind of thing, then you've got to be able to switch from one type to the other automatically, right? And so that answer your question?
It's kind of, I would just add on top of this. So looking at it from the perspective of system operator, right? So hurricane is hitting somewhere on Florida. So should the system operator be worried that it would also affect other parts of Eastern interconnection, and how would that analysis?
I mean, this is standard procedure. I mean, you, when you see a hurricane coming, you don't know where it's going to hit exactly and what path it's going to follow. So everybody in the nearby area is all ready for it. And then this is the whole idea of getting ready before a hurricane hits is by making sure that one simple thing is generators. You turn on all your generators, right? Even if they may be at zero, maybe, but it's synchronized, right? So that when the other synchronized ones dies, you start pumping up the other one. I mean, this is all standard practice. I mean, there are people who work this out. The other thing that is done is these agreements between power companies, local power companies, distribution power companies. When if you go down, you're down, and your crews are completely swamped. You get crews from nearby power companies to come and help. So these are very, very, there are certain things that people have experienced long enough to, when there are new things that are coming down the pike that we have to worry about. Anybody else? Yeah.
So you were saying one of the standards for resiliency was you can go down if the event is only likely to happen once every 10 years. Given that the catastrophic events that take these things down, like the hurricanes you're talking about, are happening far more frequently, is there any sort of rethinking that kind of metric? Because like you're talking about the hurricanes, maybe 10, 20 years ago, a category 4 hurricane would fall under the once every 10 years, but now it seems to be more like once every 2 years. So is there any thinking about changing that and shifting over to what you were talking about, which is recovery rather than just straight resiliency?
Yeah, but of course that is being thought about. The question is people don't agree on the level of strengthening that you would have. See, I mean, think about this. After Sandy occurred, which was 2012, all of them, lower Manhattan was out of whack, okay? Everybody gets much smarter after the fact, right? So everybody said, well, the seawalls around Battery Park should have been much higher, right? So everybody now knows that. Right? Nobody knew that beforehand. There's the same thing at Fukushima. Everybody says, why were the walls only 12 feet high? Because that was designed for a 100-year tidal wave, and so they said everybody should have known it should have been 16 feet high, right? I mean, so that's the problem. And in fact, it's actually worse in the sense that when in Sandy, because this was such a big political thing, they spent something like $60 billion to shore up New Jersey and New York shores in there. All right. Now, what are the probability that Sandy is going to hit again that area? Right. You should have probably shored up somewhere else along the East Coast. Right. So this is the problem with probabilities and so on. And so I think that my opinion is that one ought to make a decision collectively that this is the level of resiliency that you're going to design for. And once you know that, everybody knows that, everybody is willing to pay for it, then it's okay. If but this blame game after the fact, after the generators didn't work in Texas and people froze to death. I mean, the first thing they did was fire the guy who ran ERCOT. All right. So ERCOT had almost nothing to do with this thing. ERCOT actually worked pretty well. It was all happened at the distribution at the lower voltage levels and not at the ERCOT level. But that, so somebody's got to be blamed for these things. Yeah.
Regarding EVs, there will be so much EVs, there will be so many batteries. So how challenging it is for the battery?
Oh, I don't know. That's an open question. Nobody knows the answer to that. So, but let me point you to a different question on EVs. Is what does it do to the grid? You know, how do you design the grid to handle all these EVs? Because EVs are not going to happen overnight, right? It'll come in and slowly it'll saturate, right? So you'll have to strengthen I mean, most of you know this already, but a car, it takes about 2 to 3 times, maybe 3 times as much power as your house, right? So so if you have, and what is happening is in the more affluent neighborhoods, you suddenly get one guy buy a Tesla, and then they buy a second Tesla, and everybody there has 2 Teslas each. And now the transformer has to be changed, right? You can't handle, you know, 3 times as much house load that you had with that same distribution transformer for the 10 houses that you're stuck with it. And so these are sort of the day-to-day problems, but nobody's kind of figured out a logical way to approach it. You just sort of react to what's happening in real life. And the other thing is there's this whole amount of research going on about EV to grid. Okay, so use these huge amounts of batteries as a kind of but remember this, when people are saying this, remember that ultimately those EVs will have to have enough energy. Now you talked about energy. This goes back to energy. Nobody thinks about energy. We'll need as much energy as you needed when you had your diesel as your gas car, right? So you have to get that much energy out of the grid, okay, as you needed before. On top of that, if you want to feed back into the grid, you have to have that much energy more. These are rather simple things, I think, to think about. At least us electrical engineers should think about these things, even though a lot of the people writing these papers don't seem to. Yeah.
Yes, Dr. Bose, you mentioned that the integration of heavy renewables is sort of lowering the resiliency of the grid while we still have these reliability metrics that are in place. You said that it's getting worse, it's not helping. Do you think that, sort of a two-part question, do you think that based on your experience, that this going green by 2035, first of all, do you think that is really feasible? Second of all, do you think that by the time 2035 rolls around, that we're going to be sitting in the same situation going, well, now hindsight is 2020 and we should have done it this way, and maybe we should have changed the standards, because from now until then, things still continue to change?
Yeah, I don't think that going green, going to EVs, we should stop, right? Okay. Going with all this transformation of the grid is necessarily making it less resilient. Okay, because in fact, having generation in the distribution system gives you a better chance of microgrids. Okay, because without generation, you can't have a microgrid. The main thing about a microgrid is that you don't get the juice from the power company. You have your own. So that part, resiliency is not the question. The big problem is the one that you raised. Is it even feasible to do 2035? I think engineering wise, is it feasible? Right? I think it can be done. But I don't see that politically it's feasible, because you can't do this kind of turnover of changing 60-70% of our generation completely, okay, without changing the permitting process. Every time you hear about there are local rules about where you can put wires. There are local rules about this and that, and there's if you're going to do it that way, the speed at which we do things, if that doesn't change, there's no way we're going to hit our targets in 2035. Engineering wise, I think, even though I pointed out all the things that we don't know how to do, I think we can work it out. Okay, the part about installing generation is already worked out pretty well. Now that there would be better ways to do it. They're probably going to have some break in the battery cost of batteries. That would help the transition, because without batteries, we're not going to, without lots of batteries, lots of storage, we're not going to be able to make the transition. And so the cost is another one that people don't talk about. And probably the worst thing that the politicians do is they, even this campaign season, there are people going around, politicians going around saying, we're going to have all green energy and it'll be a lot cheaper because solar panels are so cheap, right? And you never know where they're coming from.
Maybe I can end this with the final question. Do you think the dialogue around nuclear will change as we are pushing aggressively?
Well, yes. So, I mean, from my point of view, I think it ought to change, because I don't think that without nuclear, we're going to meet it, right? So the question in my mind is that we always get sidetracked. There's a big push for fusion, okay? It was only last year, I think, that the fusion researchers could go break through the energy barrier. That is, the input energy was less than the output energy only 2 years ago. So there's a long ways to go to fusion. But there are a whole bunches of stuff that are going on the regular side. See, you can build nuclear generators. I mean, people are building them all over the world. It's only that it's all politics whether you're going to build nuclear generators or not. Germany won't, but France will, and then Germany will import French nuclear generation. I mean, it's all politics. There's no engineering reason for this nonsense. But there are new things happening. They talk about these smaller nuclear generators. Okay, now people think of small nuclear generators and think they'll carry it around in their trunk, but that's not the case. They're about 40-50 megawatts is the smallest module that I've heard of. So there are ways. The big problem in the US is going to be, again, politics. Right now, no bank will fund it. In fact, these two reactors that are coming up in the south, I said, they basically got the money for it, came from the bank, but the loan was guaranteed by the federal government. All right. So this is the problem, is that the banks don't believe that they won't be litigated to death. There won't be lots of political things thrown on the way. So that's the part that's, again, not clear to me. So nuclear, but there is a push. I think slowly it's occurring to the top level decision makers that without nuclear, we're not going to get there.
All right. Thank you, Dr.
Thank you.
Bose.
Thank you.
Thank you.
Rest of it.